Welcome to our monthly community meeting. For those of you who haven't been here before, we meet every third Tuesday of the month, unless there are other events like the OpenXLA Summit, and I'll talk about that a little more later. So typically we start these meetings off with introductions of any new contributors who are joining us for the first time today. And if you'd like to introduce yourself to the community, please feel free to chime in and share your name and, if applicable, the organization or company that you're working with.
Hello, Fia.
Hi, Hong.
Hi. Hi, everyone. My name is Hong Rong. I'm from Sci5. Currently, we are working on OpenXLA RISC-V backend. I'm based in Taiwan. If you guys feel interested in RISC-V, you can contact with me. And next month, we will also attend the summit, so you also can find us there. Nice to meet you.
Nice to meet you too. Anyone else who's new?
Hi, I'm Cyril. I'm not new to Google, but I'm new to that meeting. And my team works on OpenXLA, so I want to know what's going on.
Welcome. All right. And for anyone who doesn't feel like speaking up live in the meeting, feel free to introduce yourself on the Meet chat if that feels more comfortable to you. All right. So we kick off these meetings generally with a statement of what OpenXLA is, what the mission is that we're all driving towards. OpenXLA, in the OpenXLA project, we're building an open state-of-the-art ML compiler ecosystem collaboratively with the hardware and software communities. And instead of diving into our regular communication channels, which you can find on OpenXLA GitHub in the community repo, which is OpenXLA/community, we're going to get right into some updates from the community. And the main community updates that we go over in these meetings are active RFCs, where we'll share links to requests for comments, which are basically, open design docs that project maintainers and developers are looking for community feedback on. And I'm not sure if we have any RFC authors who want to specifically call out the RFCs that they're working on or from their team. These look mostly to be related to stable HLO, in case, Eugene, I see you're on the call, in case you want to talk through them quickly.
Yeah, sure thing. Thank you, Thea. So we have lots of RFCs, not just stable HLO related. There's also the next slide, which we'll get to in a minute. But on this slide, we specifically focus on RFCs for stable HLO. You can see the topics that are being actively worked on at the moment. Since the last month, there's been progress on making progress. There's been progress on the reduction RFC. Reduction op itself seems to need a few changes to accommodate quantization. If you're curious about how this looks like, please click a link. There's also joint work on compatibility with TOSA of this whole thing. And we're also planning to look into GPCQ, although that will need to happen in Q4. Probably won't be time in Q3. As far as extensibility and compatibility goes, these are the two RFCs important for the adoption on mobile. So that's an interesting avenue that opened up recently. There's been a post on OpenXLA Discuss. Yesterday, there's been an update on compatibility RFC, the feedback from the TFLite team. Composites are under discussion. Dynamism, sparsity, this is something that hasn't seen progress since the last meeting. Planning to follow up in Q4. Next slide. So here the first two items still related to HLO, stable HLO, can talk about them very briefly. The first one is about extending the interpreter dialect. This is something that we've been relatively quietly building up, the stable HLO reference implementation. It's actually almost ready. 91 out of 96 ops have reference implementation, so that's really nice. And this RFC is about extending specifically the reference implementation functionality. Finally, there has been a proposal also from the CFLI team about reorganizing canonicalizers and folders for MHLO. If this is something that you're interested in or could be affected by, please take a look and provide feedback. Eugene, maybe you can say a few words about the final two line items.
Yes, I will have a slide, so I think we should be covering the last two items in the slides later.
All right. In that case, I think this is it as far as RFC updates go. Anything that we missed, please let us know.
Yeah, and if you are working on any open RFCs, just a reminder to email OpenXLA Discuss. That's our main channel to signal boost RFCs in the community that have been open on GitHub. And that's a good place for anyone who wants to follow along with RFCs in the OpenXLA project to join the OpenXLA Discuss mailing list where these are typically announced. Awesome. All right, so I'm not sure if we maybe covered this last meeting, but just as a refresh, we've established the first formal group of OpenXLA core maintainers. We opened an RFC about it a couple of months ago, I believe, or maybe just 1 month ago. Please feel free to take a look and also take a look at our project governance doc. Which describes basically our open source governance in the OpenXLA project. Next steps that the core maintainers are working on right now is how our process for adding new maintainers, as well as our universal RFC process. Right now, it's a bit informal, and it might be helpful for it to be a little more organized and structured with clear expectations around how we communicate RFCs, where they go, and stuff like that. And we'll also be looking at rolling out module governance, which is basically the second layer of governance, focused more on like the technical aspects of the project and decision-making happening by maintainers at the repo and module level in the project. So I'm going to move along from that. And again, I think we covered this last time, but please remember that we have a fall summit coming up in October on the 18th and the 19th. I believe this is going to be specifically in Sunnyvale this year. And for more information, as well as our CFP and registration details, please subscribe to OpenXLA Discuss, where you can find more information about the event that we've published recently. We really hope to see you there, and especially if you're interested in presenting, please do take a look at the CFP and submit a talk proposal. We had an awesome summit with about, I think, 80 people in person, another 50 people online this spring. That was a one-day summit, and this year we're going to extend to 2 days, which will allow us to add some tutorials on common use cases in the OpenXLA project. So super excited about that and very much hope that you all can join us. Here is a preview of the agenda topics we plan to cover. We're going to be talking about major updates on PyTorch compatibility, XLA performance, and open source developer experience. And we'll be looking forward to getting ecosystem updates from some community members from Alibaba, Intel, Nod, NVIDIA, and the JAX project, as well as breakout sessions on PyTorch and ODML. And we've carved out more time than last year in the agenda for networking, hallway conversations, and open house style questions and answers for the presenters at the summit. And also on day 2, as I mentioned, we'll have more kind of roundtable whiteboarding sessions similar to what we did last year, more presentations focused on tutorial type content. And yeah, it will be great. And I believe that's all we have for the summit content. So now we've gone to the technical update section of the community meeting. And I believe I'm handing this over to you, Eugene. Is that correct?
Yeah, thank you.
Awesome. Go for it.
So yeah, I'll give you an update on the IREE Runtime prototype, what we've done, how it works, and what are our plans for the next steps. So the runtime for XLA means, so if we have a stable HLO as an input and we have HLO compilation pipeline, and in the end of HLO compilation pipeline, we have an HLO plus scheduling and bufferization, and then we pass it down to runtime. And runtime takes care of launching kernels on device, library calls, and orchestrating work on device. So in XLA, Stream Executor is not the runtime, but PJRT runtime plus Stream Executor is the runtime. And on IREE side, the HAL hardware abstraction layer plus the IREE VM is the runtime. So the HAL module plus HAL implementation, CUDA HAL is the runtime. The next slide, please. So low-level GPUs for low-level APIs for GPUs, they are converging. So if you take a look at the latest APIs in Vulkan, Metal, CUDA level 0 from Intel, they all allow common buffers, device queues, and roughly the same synchronization primitives. So the idea that you should be building work ahead of time on the host and submitting to the device with one API call, because round trips are very expensive and kernel at a time, it doesn't work. The next slide. And the next slide. So let's, for example, take a look at JAX to stable HLO lowering. So we have a simple JAX program on the left, 2 dot products, and then a sum. When we convert it to stable HLO, this is pretty straightforward. 2 dot general operations, and then stable HLO add in the end. And everything is in tensors. The next one. When we compile from stable HLO to HLO, so we convert from stable HLO to HLO representation, and then inside the HLO compilation pipeline, XLA does optimizations and buffer assignments. So this is how the HLO model looks like after XLA is done. So we have 2 Triton.gem computations. So we pick Triton to call gen.general operations. Then we have a fused computation within a single add operation. This is the last stable HLO add. And we have the main function that you have 2 Triton gems. And in the end, you add 2 results of Triton gems. So buffer assignment, it is not materialized in the IR in HLO, but it's always there in the background as in memory representation. And we also have a schedule how, in what order we run these operations. So we always run Triton gem.3 first, then the next one, and then the wrapped add operation. The next slide, please. When for this prototype, we added another IR, XLA runtime IR. So this is the MLIR dialect that represents XLA GPU program that is compiled to Kubin PTX and that has a device buffer assignment and a schedule. So if you take a look at this IR, so in the bottom we have XLA module PTX with executable exports. So we have a single module device for NVIDIA GPU. This could be in PTX, and that module contains multiple functions, and we have information about functions. Is it read, read, write? How many arguments are they read-only, write-only, read-write? And the buffer assignment, it is encoded in SSA as is SSA use dev chain. So if you take a look at the first gem, Triton gem.3, you see that we read from tensors 0 and 1 and 2, and we write into the tensor 2. And the same for the second gem and the last operation. And if you take a look at the argument, second argument is XLA output. So it means that in XLA, we always pass arguments as input buffers. So when we write to the tensor that is constructed from argument 2, it means that this is the operation that produces the result. And the last one, the last XLA dispatch, when we dispatch ref add, it writes to the fourth value. And if you follow the useDef chain, you will arrive to argument 2. The next slide, please. And when we lower this representation to IREE's stream scheduling abstraction, so IREE has a stream dialect that encodes concurrency and dispatches at slightly lower level than we have in XLA. So in this particular example, stream analysis can recognize that we have two Triton gem.dispatches that read and write to non-overlapping buffer ranges. And it means that IREE can put them into a stream concurrent region. And it means that these two operations can run concurrently on device. And after completing these two concurrent operations, we go to an add operation. The next slide, please. So after stream dialect, we go to the HAL commands, and eventually for NVIDIA backend with CUDA HAL, it becomes a CUDA graph. So in this particular example, we have two dispatches, two Triton gem dispatches. Then we have a barrier that means that, okay, we have to wait for the completion of the previously dispatched operations, and then we dispatch an add operation. So for CUDA, we get a CUDA graph with this structure. And it means that when we submit this CUDA graph to a stream, CUDA driver internally can run this two Triton gems concurrently, and it happens transparently to us. Is CUDA driver handles all the concurrent details. So we don't know about how many streams we have. We see only a single stream of execution, but the CUDA runtime itself can run this graph concurrently. The next slide, please. So this is how it is integrated with the XLA GPU. So we have JAX, TensorFlow, PyTorch at the top level frameworks, and they all talk to XLA through PJRT client. And internally inside XLA, we have this thing called executable, and it encapsulates all the data required for running PJRT executable. So PJRT executable is mapped one-to-one to XLA GPU executable. And inside the XLA GPU executable, we instantiate an IREE VM virtual machine instance, and we load two modules into the virtual machine. So the HAL module that implements command buffers, semaphores, and dispatches, kernel dispatches, and it relies on low-level CUDA HAL integration on top of CUDA. And we also load the XLA GPU IREE VM module that provides integration for libraries, cuBLAS, cuDNN, cuFFT, custom calls, and like that. And it relies on stream executor low-level abstraction. So both of these modules, they reuse the same CUDA context, and they can reuse the same CUDA stream, or they can create multiple CUDA streams. But they all are inside single VM instance, and they can talk to each other, pass buffers to each other as IREE buffers or basically pointers on device memory. The next slide, please. Yeah, CUDA graph limitations. So why are we doing that in the first place? Because CUDA graphs, they have limitations that we have to work around to get performance. So CUDA graphs have no arguments. Once you capture an argument, capture CUDA graph, the only thing you can do is run it exactly as you captured. So all the pointers must be the same, the graph structure must be the same. You can't change the kernels, you can't change it cheaply when you launch the graph. Just exactly as you captured. So in the real shared environment with multiple models running concurrently, you can't guarantee that your model will be getting the same pointers from request to request. So your pointers will change on every request. If you have the same model running multiple concurrent requests, then again, it's too hard to guarantee that all the pointers will be the same. So inputs naturally have new pointers on every request. But then in XLA, we also have a temporary allocation. This is a large allocation that we use for allocating temporary values inside XLA computation. And it's very hard to guarantee that temporary allocation will get to the same pointer. If you're lucky, yes, you can get the same allocation. And if the temporary allocation is roughly full, it's exactly the same size. So this bucket is in different buckets in BFC allocator. So maybe if you're lucky, you'll get the same pointer. But in practice, it happens, almost never happens, especially in a shared environment. And so right now, CUDA graphs work really well for the LLM models that we have, because most of the LLM models today have some decoding step in the beginning and then a while loop that produces tokens. And inside the while loop, by construction, it is guaranteed that all the pointers will be the same and we don't have to do any graph updates. But if the model doesn't have while loops, then it's almost certainly that on every request you have to do graph updates. And there are two APIs for building CUDA graphs. So right now in XLA, we rely on Graph Capture API. So we basically turn on the CUDA stream into graph capture mode. We replay the XLA computation, and we trace what operations XLA computation recorded on the stream. And then we capture the trace into a graph that we can later execute. And the second API is when you build CUDA graph explicitly. So CUDA graph is just a graph, a DAG with the nodes and edges. And instead of tracing execution of XLA computation into a graph, you can use explicit APIs and build to the nodes. So you have much better control what is the graph that you're building, and especially for multi-streaming, you have a perfect control how many edges you have, what is the dependency structure, how much concurrency you can allow in the CUDA graph. So what we really want to do for XLA is to use the second API, build graphs explicitly. And this is how CUDA HAL works in IREE. The next slide, please. So we did some performance evaluation on two models, two LLM models we have internally, like a small one model and the larger one. So I can't tell you how small and how large they are, but in billions parameters. So the thing is that the reuse all example is when your pointers don't change. So you build the graph and then you always reuse the CUDA graph. So we were able to get some performance improvement from CUDA HAL integration compared to the PJRT, the current CUDA graph integration in the XLA, and the Thunk. This is the old runtime in XLA, which is interpreter based and doesn't have CUDA graph integration. It executes kernels one by one. So it is up 20% faster than Thunks. The update once example, this is when pointers change only once when you call the XLA executable, but then inside the loop pointer stays the same. This is roughly what you get at inference for models with while loops. So you see that compared to PJRT graphs integration that we have today, we have about 13% speed up, and speed up versus Thunks stays the same. And the last two rows is update all. So this means that what if CUDA graphs always have to be updated, even inside while loops? So this is not realistic for LLM models we have today, but imagine that in the future we have LLM models without loops, or we have to unroll loops for whatever reason. And then CUDA graph update becomes much more expensive. So 24% more expensive on a small model and 11% more expensive for a large model than current CUDA graph integration. So the key takeaway that you can get really nice speed up today in ideal benchmark environment from current CUDA graph integration. But in the real world, when data and pointers changes all the time, we have to do better than what we have today. And the next slide, please. So instead of bringing IREE, HAL, and IREE to XLA, what we want to do is to bring the ideas from IREE that we proved that work well and bring performance improvement to XLA. So the first one, the biggest one, is we know that command buffers, they do work. Command buffers is a good thing. So we want explicit command buffers in XLA. So I have documented the link. This is roughly 13, 14 milestones for the tasks that we want to accomplish to bring command buffers and other improvements to XLA. But the biggest one is adding command buffers to Stream Executor and adding command buffer abstraction support to HLO and building photographs explicitly. So we will add command buffer opcode to HLO probably, maybe as a custom call first, but basically the HLO compilation pipeline itself should be able to find the regions that we can put into a command buffer. And within a region that is inside a command buffer, XLA can do buffer assignment that is optimized for concurrency. Because right now, all buffer assignment is done assuming that we have a single stream of execution, and it tries really hard to minimize the memory that XLA computation uses. But concurrency is basically a trade-off. You use more memory, but you have more concurrency, and you can build a DAG with more concurrency in it, or you optimize for memory, and then your photograph in the end will be mostly straight line. So we want command buffers to be explicit in HLO in XLA, have like first-class support as an HLO opcode ideally, and then we can build some of the scheduling and buffer assignment inside XLA optimized for photographs. So we know that explicit photograph construction and update APIs, they have near zero overhead compared to retracing. So we want to be using command buffer abstraction to build and update photographs explicitly. And also we want to use a specialized interpreter runtime. So right now, XLA runtime, and that was called PJRT, it uses LLVM JIT compilation to compile the host function that builds photographs, that launches kernels, that launches library calls, and all that. And for what we use LLVM JIT in XLA, it's too big hammer. So we don't need all the features that LLVM has. And it's hard to debug. So if something goes wrong, you have to debug how LLVM JIT compilation works. Also, it can be slow because we create programs that are unnatural for LLVM. Is the IR that we produce for XLA is nothing like the IR you can see from compiling your C or C++ program with Clang. So sometimes we have to fight LLVM to make it fast. So we want to bring all the features that we have in current XLA runtime and bring them back to Funcs and Stream Executor. And while we're doing that, we want to simplify the overall stack, because right now we have a lot of abstraction layers and a lot of complexity accumulated over the years. So we plan to clean that up as a part of this project. So the plan is to start, the work started on this already. So I think that by the end of the year, maybe Q1 in January, we should be able in a good shape, and we should be able to switch XLA to this new runtime and remove some of the old code. The next slide, please. So the things that we have in XLA runtime today that we never implemented in Funcs. First of all is AT compilation and serialization. So because we use LLVM for JIT compilation, we just save the object file that we produce in the end. And this is the artifact that we can save on disk, ship over the network, and in a few milliseconds instantiate it back into XLA executable that we can run. So we will be adding serialization support to Funcs. Probably this will be Protoype based. So you just encode your interpreter. Well, if you think of Funcs as interpreter, you just encode your interpreter IR in Protoype, and then plus PTX plus Kubin, plus all the data required to recover XLA executable back from Protoype. Also in XLA runtime, we have typed custom calls, which are called FFI. So in current XLA custom calls that are widely used, you get void star pointer for every argument, and you have no idea what is the type of the buffer. So you have to encode it yourself. So you have to pass the sizes of the buffers, data types, all the information through this opaque bytes array on custom call, and people usually use Protoype, and it is quite unpleasant to use and can be very slow to decode. So we will be porting typed FFI to the new runtime. So you should be getting, instead of void pointers, you will be getting XLA FFI buffer. And that C struct will have, well, first of all, this will be a stable C ABI, no dependency on C++, because you want to be able to load custom calls dynamically from dynamic library. And it will be some C++ wrapper around stable C ABI that will provide some nice user-friendly features. So it's not going to be some opaque pointer, then you have no idea what's inside, but it will be a buffer plus type plus shape. And probably we will add support for some custom types. So ideally, your custom call should be able to return some of your custom value to XLA, and you should be able to pass it back to the next custom call and then safely dereference, and you should know what's inside. So it's mostly working in current FFI, in current XLA runtime, but we didn't share it widely because it was not implemented for CPU. As part of this work, I think we will be doing this typed FFI both for GPU and CPU backends. And then we will ask everyone to switch, and we'll provide some documentation how to do it. Also, some operations were never implemented in Thunks. For example, send, receive, and top K kernels, custom kernels, they're only available in the current runtime. So we'll be porting all the features that were never implemented in Thunks back to Thunks. And as part of this process, we will remove LM-HLO dialect. So right now, once you're done with HLO computation, we lower to LM-HLO dialect, which is basically MHLO, stable HLO-like dialect, but with memrefs as buffers to encode buffer assignment plus operations for library calls. And then from that dialect, we'll lower to the runtime with Thunks. So what we will be doing, we will be directly lowering from optimized HLO with command buffers to Thunks and some command buffer interpreter that we don't have right now, but it is a work in progress. Yeah, the question?
Yeah, can you explain again what is the motivation behind going back and supporting these features in Thunks?
So the decision is that we know that command buffers is a good thing. So we want command buffers in XLA. So we have three options: bring them to Thunks, bring them to current XLA runtime, or bring them together with IREE Runtime. And we think that implementing command buffers on top of Thunks as a special site data structure will be the shortest way to get to the end. So what we care about, performance. So IREE Runtime is a big dependency to XLA, and then we have Stream Executor and HAL, which is hard to maintain and requires some long-term process to migrate out of Stream Executor to HAL, because in the long term, we don't want two abstractions, two low-level abstractions per device. The current integrations with the LLVM, we have troubles with LLVM. And we don't need, strictly speaking, LLVM for what we're trying, the problem that we're trying to solve in XLA. We don't need LLVM for that. We need a simple interpreter. So based on the experience with IREE VM is nice. So interpreter is really nice. So we don't want to compile to native code when we don't have to, when we don't require big performance, and we don't need the features of the native compilation. It is much easier to maintain interpreter. So we believe that Thunks interpreter is the fastest way to get there.
I see. So what happens to all the features that you have currently implemented in the new runtime, including support for new custom calls and all those things?
We'll be migrating all of that.
I see. I see. Thanks.
Media?
Yes, if you can expand on the IREE dependency, because that got me a bit confused here. So it's a bit the same question as Jaya here, but I'm not sure I understand right now the trade-off that are made of going back to Thunk when you seem to already have something working with the IREE HAL, and also like there are people in the OpenXLA project working on IREE. So are we going to have two implementation of IREE HAL somehow or something like that? Like why aren't we consolidating our efforts?
Yes, so the problem is that now we hope that we will not end up with two IREE-like HAL. So the idea, we want to take only the command buffer. So we will not be taking the semaphores and fences abstraction from IREE. And we will not be taking queues and devices. So the command buffer will be the only abstraction that we will take. And it is about 5 to 10 API calls. And I hope that's it. Also, we will not be taking VM. So right now, we don't need it, but we're not completely giving up. Okay, we're not going to use IREE. So right now, the simplest and fastest way to get performance inside XLA is to take just the command buffers and implement it. But if we see that we need a VM, we don't have plans to write a second VM. Or if we see that we need HAL, some abstraction for Vulkan or Metal, we don't have plans to write it in Stream Executor. So if we will see, so we can do IREE integration right now, but this is a lot of code, and the features that XLA needs right now, it is a small subset of what IREE HAL and IREE VM can do. So this is a big like LVM today. We use LVM, it's nice, it works, but it is a huge dependency, and sometimes we have to pay the cost of maintaining that huge dependency. So the plan is to keep things simple for now, and also LMH low. So to bring IREE runtime to XLA, we would have 3 runtimes in the meantime until IREE migration is finished. And it's just very hard to maintain with LMH lowering all these intermediate steps and 3 different runtimes, and people keep adding new features. So the plan is, okay, let's bring XLA down to a single runtime first, simplify it, remove all the code that we don't need anymore, and then we will revisit, okay, do we need Vulkan or WebGPU or Metal integration, or do we see a need for a VM with the more powerful custom models? Because right now, even with the typed FFI, it's not nearly as powerful as IREE VM plus custom model. But
Eugene, you mentioned that you want to do that because it's faster. It's just counterintuitive to me to say that it's faster to re-implement something that's using IREE as is. I mean, I understand that IREE has more feature than you need, but it's already implemented. So I would have thought that the fastest way would be to just reuse their command buffer.
Not everything. So the prototype, the numbers that I show, this is we have a special.
You
part.
said faster to get there, right?
Yeah, faster to get there.
But
because the results, the prototype is not like stock IREE. This is IREE with some local patches that will have to be productionized first. And productionizing that local patches is also quite a lot of work on the IREE side.
And you think it's more work to do that than to just re-implement everything in Thunk and migrating to Thunk?
Yeah, it's definitely lower risk and less work and more confidence. So I'm 100% confident that this Thunk migration will be done and it's going to work, and it probably will be done this year. The IREE migration, probably Q1, Q2, realistically, and more work.
I see.
And also, if we're done with that integration, so we remove one runtime, we remove element flow, then we simplify our path to get to IREE if you want to. So instead of this LMH low, XLA runtime, IREE dialect, once we get rid of LMH low, we can directly lower from HLO plus command buffers to the low-level representation of IREE. Because right now, I have to fight IREE because IREE is built around value semantics and IREE does some bufferization. So it's quite tricky to pass XLA bufferization to IREE. So IREE wouldn't make some other decisions that would screw up bufferization.
Okay.
Once we have simplified IR and more direct path to lower level abstractions inside IREE, it should be easier. So I think if we do that, and if we want to do IREE, we still should be able to do it by Q2. But in the meantime, we should have a simple stack to work with.
Okay, thank you. And about the LMHLO aspects, like right now, this is the only format we have to serialize the HLO, the optimized HLO plus the buffer assignments.
Right now, yes.
It's not clear to me in your plan, because you just say we'll remove LMHLO. It's not clear what's the replacement here.
We don't, so we'll go directly from HLO to thunks interpreter and command buffers. So
But you see that we're losing the only format today that we have that is a proper serialization input to the backend.
Yes, but I think right now the only backend that we relies on LMHLO is XLA runtime, and it should be fine to emit XLA runtime directly. So LMHLO is like one of the first IRs, MLAR dialects designed. It's not the best design. I think right now, if we would be designing something like that, it would look like XLA IR that I showed earlier with SSA use dev chains to encode buffer use and probably tensors. So I think memrefs, it's very hard to do some analysis. So this is an intermediate step that doesn't bring much value today. So we think that will simplify the stack if we get rid of it.
I have some concern about this. I think you should send a separate RFC that we could discuss on that and look at it. I think we won't get to it in this meeting because I don't want to hold the floor, but that's probably something that I see as important right now. You should discuss it.
Okay. Yeah, I'll send an RFC, you can discuss what are the concerns.
Thanks.
Do we have time for a few more questions?
Yeah, I think so.
I have a couple more questions. First thing is that you're going to add support for multiple streams into thunks.
No. So we will still have a single stream in thunks, at least initially. We will do multi-streaming through choreographs, command buffers. So command buffer can use multiple streams, but you never explicitly use multiple streams in choreograph. Choreograph always submitted to a single stream. So we plan to have single compute stream in XLA for foreseeable future.
Okay, and my second question was then, is there any changes required to your choreographs infrastructure for thunks then now? Because
it will be a big rewrite because instead of graph capture, we will be using graph construction.
So you're going to implement the choreographs graph construction in thunks, right? So the capture is going.
Yes.
Or if you want to do a capture, you're going to capture thunks then.
We don't want to do capture because we see a lot of bugs from captures and we see performance problems with captures. So we want to build choreographs using graph building APIs.
I see. But if you had to, you would have to then do the same thing where we started, like
yes,
capturing thunks and okay. Yeah. Well, so any timeline on when we can kind of, I mean, is the code already up there, or do you plan?
I have few first pull requests opened yesterday, so just starting. So it's super fresh.
Nice. It'd be interesting to follow this right from the inception. Thanks.
I think we should leave some time for the next presenter, right? Or can we take more questions?
I think, let me take a really, really quick look. Oh, let's see. I think that, so porting, sorry. I think that there are a couple of more slides here on your presentation, Eugene, but I think that
I'll go to the next one then.
Yeah.
Okay, yeah. So this is how it's going to look like. We call it thunks ++. So in the green box, these are the thunks that we have right now, Gem, Convolution, Collective, and we will add the new kind of thunk, command buffer thunk. And the yellow box on the right, this will be a parallel universe of command buffer interpreter So we will be building some in-memory data structure to dispatch kernel, copy buffer, insert a barrier, and that data structure will be building a CUDA graph. And they all should talk to each other and build kernels plus CUDA graphs. And I think this should be lightweight and definitely should be ready by the end of the year. Or probably it should be ready in a month, but I expect that it will take some time to launch it in production by default. And do we have another slide? Oh, yeah, and then it's PJRT. Then it's not my slide.
Is someone from the PJRT team online to take this one?
Yeah, so this is Jieying from Google. Yeah, and I'm going to give a...
Yes, thank you. Sorry about that. I assumed it was part of the same presentation.
Cool. Yeah, so this is Jieying from Google, and I'm going to give a quick update on PJRT. So we have a versioning and compatibility proposal. PJRT API is going to have a major version and a minor version. And for minor version updates, we were proposing that the framework will provide an N-week forward compatibility window to support an O plugin. And as a start, the N-week will be 6 weeks. And for major version updates, the first major update will be between 6 to 12 months. And after that, we will aim for updating it once every year. And the frameworks will not support an older major version plugin. Is that a question? Yeah, sorry. Okay, cool. I'll continue. And then for the case that a plugin is newer than the framework, it will be up to the plugin to define what the behavior it should be. And we have a planned CAPI changes that we are going to add profiler CAPIs. Okay. Cool. So that's all from the PJRT CAPI updates. Any questions?
Oh, sorry. Yeah, any questions?
Maybe one quick question. Like, there's a link on the slide. I don't have the slides yet, so I cannot click on it. Is this like all publicly shared?
Yeah. So the doc is so the link for the PJRT one. The link is the OpenXLA public folder.
Okay.
Yeah. So it's open. It's like read access to everyone, and you can request like comment if you need it. Cool. Thank you.
Thanks so much, Jieying. Okay, I think that was our last presentation. So one quick note, because we're having the OpenXLA Summit that falls in the normal time, we would be kind of around the normal time we would usually have this meeting. I think we will probably be skipping the October community meeting, and I'll send an email just to make sure everyone is aware of that. And then one other kind of housekeeping point is we're thinking about moving this meeting an hour later. It overlaps with a lot of folks' commutes and or childcare responsibilities, and we want to make sure that we make it easy for people to attend this meeting in the future. So again, look out for meeting updates about our November meeting, which will likely be our next one. Other than that, please reach out again in case you're interested in presenting at the OpenXLA Summit happening on October 18th and 19th. We have details in OpenXLA Discuss about how to register or sign up to present. And again, if you're ever interested in presenting at this meeting, please indicate your interest on either the OpenXLA meeting notes or by emailing me or any other member of any other maintainer in the OpenXLA project, and we can talk you through how to sign up to present at a future meeting. I think the last question is from Jaya. where can I find the link to doc again? Jaya, I'm going to make sure that all the doc links that have been mentioned here end up in the community meeting notes file that is attached to this meeting invitation. Just to make sure that there's a clear way to access that information. And as always, we'll be publishing the slides and linking to them also from the community meeting notes. Thanks so much for joining.